Okay, welcome back everyone. So rates of change, kind of continuation. You're learning about rates of change in the beginning of advanced functions. And so you kind of define what a rate of change is. You go into instantaneous rates of change. You tie it in with tangent lines to certain functions. And now what I want to be able to do for you is try to relate those rates of change and give you some kind of a meaning behind. And one of the most common ones that is utilized in school is that all of us can visualize displacement in some way. So displacement in terms of a distance covered, or maybe a height which is covered, or depth or something, or width or something like that. So some kind of a displacement where you're changing, okay, some kind of a distance. And now if you're going to be traveling some kind of a distance, then you're going to have a particular speed. Now, once you get into advanced functions, all of us have a concept of speed because we have seen people walking or running, jumping, driving in cars or airplanes. So we understand, the faster that you go, so the faster your speed is, the faster you're going to cover, okay, that displacement, so that distance that you want to be able to cover. So it's going to take you less time. So let's take a look in here because I want to make that visual and then also put it into graphs so that you can tie in the physical sense, okay, of covering some kind of a distance or displacement, and then putting it on a graph and then seeing that speed, okay, so that what we call kind of speed is basically just the rate of change to our actual distances, right? So that's what it will be. So I like this example because I utilize kind of sports. And if you think about the 100-meter race, so if you're going to, let's say, Olympics and you're watching the 100-meter race, some of you may know that, the top sprinters will be able to cover 100 meters in about 10 seconds, sometimes even less, which is pretty crazy how fast that is. Now, what they're doing is they're covering that 100 meters. So there's a distance to cover. So it's a displacement of, let's say, 100 meters. And they're starting from the starting block and then ending at 100. And what we would see, okay, is that any sprinter would kind of take off in the beginning. Their actual speed is going to be 0, right? Because they're just standing still. But then they're going to be picking up speed until they get into their kind of maximum speed, and they're going to try to maintain that for the rest of the race until they cross the line. So if we would visualize that in a graph, okay, that's what I want to be able to do, and then I can tie it back into these rates of change, going back to that secant, okay, and then finding an average rate of change between, okay, two particular points, and then, talking about instantaneous rate of change, and then the tangent, which might be a speed at a particular point, okay? So what speed are they covering at a particular point in time, okay, as they are covering that 100 meters? So how would that look like? So let me just kind of draw, okay, a graph in here. So what we would have is, we would have kind of something like this, where, we have our X and Y axes. Now I'm going to graph it in this way, and let's say that, so this is what we're taking some top sprinter, okay, so it's going to be 10 seconds. This is my time t, okay, this is the displacement or the distance d, okay, going in this direction. And I can kind of write this in and fill in all the kind of blanks in here. So a runner, okay, so starting, if this is my 0, okay, and then this right here, let's say, is 100 meters, okay, so this is my distance. I'm going to put brackets in here in meters, and then I'll label this so that it kind of looks like a correct type of graph that you would have to do in school, okay, with your axes. So what happens is that initially, okay, so we're starting at 0, and then we're going to be taking off. So for the first few seconds, all sprinters, they're going to slowly try to kind of take off in here, kind of in this direction, right? Now, I'm going to redo this because it's not a straight line. It just kind of goes like this, right? So you'll notice that, they're just taking off. So there's their actual distance that they're covering is not a lot, but then they're going to be starting to quickly, cover this distance. And then, so at some particular point, let's say maybe somewhere here after a few seconds, then they might get to their final speed, all right, and until eventually, you know, maybe later on they kind of taper off because as they get tired, all right, so then they'll get to their 100 meters. So this is my around 10 seconds, okay, and then this would be the 100 meters. Of course, they still continue because it's not like they stop running, right? They just go through the line, so they continue on. But we want to just be able to kind of see this 100 meters being covered. And now, so this is our displacement. So we're displacing from zero, our starting point, you know, to 100 meters. And if we want to know what the speed is, so this the actual speed, okay, is defined in the following way. So we have our speed, which is equal to, so typically we have kind of, if you remember, absolute values. So it is the change in your displacement, okay, divided by kind of the change in time. So notice that this is nothing else but just a rate of change. So you have your independent variable, which is time, and then your dependent variable, which is distance. So depending on the time that this runner is going through, you know, this particular distance is going to be different. So we're going to start at 0 and then we go off. Now, if we took, okay, so if we wanted to, I mean, we certainly could have, right, in terms of rates of change. We could have taken this point and then we could have taken this point. Okay, so let's say if it was actually at 10 seconds exactly, and we could find, so notice that now my secant line would look kind of weird, but it would be looking like this, right? Because that's my secant line. Now, every runner initially, okay, is not going at a constant speed, right? So my secant line would mean, so in this case, that would have been the constant speed. So constant meaning unchanging. So clearly our speed is changing as we're running. Initially, you know, we're just kind of taking off, right? And then we start to speed up. So you notice that in here, and this goes back to the instantaneous rate of change, which would be like your instantaneous speed, okay? What are you moving at, okay, as you're moving, okay, along and you're running? It's like looking at the speedometer in your car. So if you're in your car, okay, and you're looking at your speedometer, it's, let's say, displaying 120 kilometers an hour, that's your instantaneous speed. It's trying to measure over a very small interval, okay, the rate of change of how you're moving within that car. So the same thing here with the runner initially, okay, the rates of changes, the instantaneous rate of change is not very quick, but then it just kind of goes off and then it levels off until you probably, the runner kind of gets tired, and then later on maybe they slow down a little bit. All right, so that's what you might see within here. So if I wanted to know kind of the instantaneous rates of change, I could have definitely, you know, picked a point right here, and then it's almost like drawing a tangent line, right? So I'm going to try to put that tangent line in there, okay, and that would have been my instantaneous speed at that point, okay? Now, from here, these instantaneous speeds, so these tangent lines, okay, I can take this graph and I can create a speed graph, right? Where I am just taking the actual rates of change, okay, and seeing what is happening throughout, okay, in this entire thing. So in the beginning, okay, my speed is very low because I'm just taking off. So my instantaneous speed, it would have been like a tangent line or a slope of almost 0, but then it just starts to increase. And then eventually it kind of looks like it's kind of straight. So all the way maybe from almost, you know, let's say around here, let's say all the way maybe until about there. Okay, if I try to draw a line, okay, across here, notice that it's pretty much kind of constant. That's what you have. So you would have along that stretch, it's constant. And then again, it looks like the runner kind of, I'm not saying every runner gets tired, but some runners towards the end may not go exactly in the same speed. So they're accelerating, they speed up, okay, and then they maintain that speed as long as they possibly can, okay, until they finally finish the race. So this is how we actually define our speed, okay? So it is the change of the displacement over the change in time, all right? Now, if I was looking at this, okay, and I wanted to now transfer, so I'm going to try, okay, I'm going to try to transfer, okay, this graph. So let's say, I know this is not going to be, but I'm going to duplicate it, and let's bring it down, okay, a little bit. Okay, I'm going to try to, let me remove this from here, okay, and remove that. If I now take these, okay, and instead what I would do is right here, I'm going to now label that this will be my speed. Now this is going to be, in this case, it's meters per second, okay, because I'm running in meters, okay, the time traveled is in seconds, okay, and then in here, so if I put, let's say this was my 10 seconds, this is my time, okay, so that I have in here in seconds. If I wanted to, now initially, so from this point, I know that the speed was 0, right? Now at this point right here, it looks like my speed, okay, is kind of increasing, right? So it looks like it's kind of increasing up. So if I was drawing up to this particular point right there, so I know that my speed that I am moving at would kind of be increasing. Now, it may not necessarily be increasing at a constant rate, but it's definitely kind of increasing. Now, in here, notice that from this point to this point, it looks like it's even increasing more. So I have a faster rate of increase. It's almost like it's starting to increase a lot more to some maybe maximum, right? Some maximum speed that I can attain. Now, from this point to this point, and this is always tricky for students to realize, it looks like my speed is constant, like it's just staying. I'm no longer increasing it, okay, any further. So, you know, right here, it would have been kind of like a straight line where I'm trying just to maintain my speed. So I am increasing it in the beginning, okay, because I'm taking off, then I'm really kind of increasing it, and then I'm trying to maintain it. And now notice, you know, like, so from, let's say, maybe from here to here, you know, it looks like now I'm slowly slowing down. Now, of course, okay, in terms of the slowing down, you know, so this is right here. I'm going to plot this down. So it looks like my speed is kind of slowly coming down, okay, and then eventually, you know, it looks like, you know, I've kind of hit that 100-meter dash. Now, we don't know exactly what happens afterwards, you know, okay, obviously, if I just drop to here, so it's probably going to look maybe something like that, okay, and then I might just be decreasing my speed entirely, okay, until eventually, you know, so this maybe looks like that, and then I just get to 0, meaning that, you know, the runner just kind of, whoever wins puts up their hand and just kind of comes to a stop, right? But they've still covered some distance. So this is interesting because it allows you to map between speed and the actual displacements that happen, all right? Now, I'll give you another example with these kind of speeds and displacements, okay, with respect to height, which is definitely one which students study when you are doing quadratics, you know, like when you're doing parabolas. So, you know, thinking about throwing up a ball or something like that, you know, you can definitely relate it into a graph. So if you're standing around, so I'm going to kind of say, okay, so this is me, okay, you know, smiling, doing some math, okay, and I have a ball, okay, and I toss this ball up, okay, so it goes all the way up. Now, we know, we don't have to know necessarily physics, but just from understanding, if we're going to try to toss this ball as high as we can, eventually it goes really fast because initially we try to launch it up, and then we notice, like, hold on a second, slowing down, and then it just pauses, right? It just gets stopped in the air somewhere, and then it just starts coming back again, right? So that's what we see in here. So if we were graphing that, okay, now in this case, you know, it would have been, I'm going to call it height. Okay, so let's say this is height. It can still be displacement d. Okay, and let's say it's still maybe in meters because I don't think I can toss it up in kilometers up. All right, and then this is, you know, some time. Okay, maybe in seconds. So how would this look like in terms of the height? So initially, we know that we would have started from 0, right? So because that would be, let's say this is, okay, the initial starting point. So this is 0 meters up in the air, although I guess technically it can be a little bit higher because I'm standing on the ground, but let's assume that that's my reference. And now I start, launching it up. So what happens is, okay, as I launch it up, okay, initially, okay, I give it as much strength as I can. So it just starts to launch up, this way. So my fastest speed, okay, is actually in the initial launch, because after I let it go, the air, okay, because there's air resistance, so air particles is gonna hit my ball and it's gonna try to slow it down. But as you may also know, there's also gravity, which is pulling it down. It's trying to stop it and bring it back down to, to the ground. So what happens is, this thing kind of looks like this eventually, okay, and it reaches its peak, right? And it's almost like it pauses right here, and then it starts to come down again, right? So then it just starts to come down until eventually it's going to, come down and reach back, okay? So somewhere here, let's say maybe I catch it, okay? Now, it goes up, slows down, and starts coming back and increases its speed, right? So it looks like it's just increasing its speed. So actually, if I'm catching it, probably is going to hurt because it's going to be kind of almost at the fastest, okay, rate. And you see this in quadratic problems because it looks like a parabola. It looks like a parabola that's facing downward, where they have this, which is kind of your vertex at the peak, okay? And then it has your zero crossings. So your zero crossings are there. And then you can actually plot this parabola. So we can have an equation for it. Now, I'm not going to do the equation here because my goal is to try to show you, what happens to these, okay, in terms of displacements and rates of change. So in this case, if I started the drawing, okay, and finding out, of course, I can find my rates of change. Okay, so in this case, my speed that I would be looking for, okay, would have been equal to, this is now my change in the height, okay, divided by the change in the time that I would have. Now I'm putting the absolutes because, the positives and negatives, I'm just interested in it kind of, what is the actual speed at that particular point. Of course, we can give it a direction going up or coming down, okay, but for now I'm just interested in like what is the actual speed. We can clearly know if we're going to throw a ball, it's going up, it speeds up, and then it starts to come down. All right, so in this case, and if I were to draw my tangent lines, so you would have one tangent line here, let's say, maybe another tangent line here. Now you notice that here it would have been flat, okay, which means that basically my ball has stopped in the air, okay, and then of course it starts coming down. So it's going to kind of look like this, and then eventually it's going to look like this, okay, where it's coming down towards me and I'm catching it by hand. So those tangents, which are basically at particular points, are nothing else but the instantaneous rates of change. And of course, instantaneous rates of change, I'll put up a link, maybe I should have mentioned that. I'll put that above in case you forgot about it. So within these, we can measure what these are. Okay, so notice that it's the highest, okay, first, and then it looks like it's kind of slows down, okay, then it's flat, then it comes down, okay, and then it goes, okay. Now notice that it changes direction. So if you really want, because of the change of direction, the slope, the tangent would actually have a negative slope, right? So it would be something like that. So how would this look like if we were trying to draw it? So like if I kind of did this, the same thing, let's say this is my time, and now I want to know my speed. I'm going to call speed S, okay, and this is meters per second, all right? So what happens? How would this look like? So it looks like my speed initially is the highest, right? So that's what I would have. So my speed initially kind of is the highest that I would get, okay, which means that I am not going to start at 0, okay? I'm actually at time t0, okay? I'm going to start at some height, okay? So some speed, some speed. And then my speed, notice my tangent lines go flat. So it's almost like I am literally now kind of going in this direction. And so here, I'm going to try to show you. if I go all the way in here so that I do it correctly, so this kind of goes over, and here, notice that it's going to be 0 because the ball stops there. And then it starts coming down, and notice that the slope would actually be negative. So it kind of goes now in this direction until eventually, you know, so right here, okay, let's say I catch it. So I'm going to try to erase this in here, right there, so it kind of, I'm just catching it in. And notice that now you can transition between the graphs. And what I find in advanced functions, sometimes if you have, you know, cool teachers, or sometimes they call them mean teachers, you know, they might actually give you this graph right here, and then they'll say, you know, try to replicate, and they might give you, you know, what that initial, let's say, thing was, and they'll say, you know, please try to draw from this your displacement. So this really tests your ability of understanding the instantaneous rates of change. So those tangent lines, you know, so what I typically do in these cases, when I'm given that, when I was a student, I would say, okay, here I know what the rate of change is. So remember, it's just a slope. So, you know, let's imagine that this was maybe 10, okay? So 10 meters per second. So all that means is you're going to be at time t0, you have a slope of 10. So that would translate to like a tangent, drawing a tangent line in here. And then you can, you know, say, okay, well, I have another point in here, and let's say this was maybe 5, okay? So that has a different slope. So what I would do is I would go back in here, so at 5, okay, and then I would have a different slope. So I would be drawing these tangents, okay, and then I would have another tangent here, which is 0, you know, and then I would have this one, which is probably going to be -5, and then -10, something along there. And once you draw these tangent lines at particular points, you can then start approximating the displacement, okay, the height, by just connecting those points with those particular slopes, okay? So that's exactly what we would do. So we would have one which is like this, right? We would have another one which is like that. You know, we might have one which is flat, okay, one which goes like this, okay, and then another one which goes that way. So, you know, let's say, and these were the points that they were kind of joining in here. So once you know those, you know, then what I recommend students do is like, oh, okay, it's going to look kind of like this, where you're basically just drawing, okay, almost like a function which just touches those tangent lines. And then once you remove this, now, let me go full. So once you remove these lines, notice that you will have your displacement. And you can do the same thing, okay, in here as well. You know, you can take those slopes and carry them on. All right. Now, before I finish this, and I hope that these examples kind of made sense to you in terms of graphs. You know, they're not the prettiest of graphs, but, you know, I wanted to give that to you. So when you're drawing these okay, so let's say if this is I'm going to try to do this a time, and let's make this a displacement. If the lines, okay, so if you have a straight line, like a constant line, so notice that in these cases, your rate of change is constant on this interval. So it doesn't change, right? So if it's a straight line on the displacement, it does not change. Now, if on the other hand, let's say it's flat like this, okay? So if you have something like this, which is flat, it means that you're not moving anywhere, you're just staying in the same location. And clearly, if you're staying in the same location, your speed is basically stuck at 0, okay, in that particular case. Okay, so because the slope would have been 0 of a flat line. Now, if you are moving, okay, and you notice that, like, I have something which goes down, okay, now you have a negative slope, so it looks still like it's constant, right? Because if we would find the slope, it would be constant on this interval, okay, but it would be negative. So, you know, you can always relate it back, okay, and say, okay, so it's negative, okay? It doesn't mean it's 0, okay? It just means that you have a constant speed, okay? And what it means is just bringing you back, okay, almost to where you're started from. Now the trickier ones are, so not when they're constant, but when you are going to have something like this. So notice in this case, now if you put tangent lines to these, you notice that your speed is actually increasing. So you put your tangent line like this, okay, tangent line like this, and what you're noticing is that, oh, it looks like my speed is increasing in these situations. So I don't have a constant speed, I'm actually increasing my speed. And if you have the opposite, so if you're going to go in the other direction, so let's say that in this case, you have something like that, now it means like you are, so here notice, so here's the speed, so if these are my tangent lines, so notice that the slopes, okay, are less steep. So it looks like I'm slowing down my speed, right? So my tangent lines were very steep down, okay, and now I'm slowing down. And this can also happen in the opposite direction. So if you're going to go and do that, okay, so this just means you had a very fast speed and then you're slowing down, like our parabola, right, that we had in here where the ball is being tossed up. Very fast up and then it's slowing down, hit zero, okay, and then it starts coming down. So you see those instances. So what happens to our graphs tells us a lot about what happens to the actual speed or the rate of change. Now, in advanced functions, when you talk about rates of change, most of the time it will be some kind of a displacement, but it doesn't have to be physical distances. It can be many things. You can have the growth of your investment fund speeding up, slowing down, coming down, right? So you can relate it back to anything. And that's why these rates of change are kind of important, because they tell us what is actually happening. Are we increasing? Are we steady, okay, going up? Are we just flat now, okay? Whatever it might be. So that's the kind of one of the last videos, I guess, on these rates of change. I hope that it gives you some visual aspect of being able to graph these. I certainly do encourage you that you walk through the video and try to graph these things on your own and relate it back to something that you understand as well. Okay? Thanks for watching. Thumbs up, and we'll see you in a future video. Okay? Cheers, grade 12 students. Bye, everybody.